Good afternoon, everybody. You all know me by now. My name's Clarecia. I'm both a graduate data analyst with the Department of Health at the moment and a student of medical physics with you all. So my work at the moment is on target motion assessment, specifically looking at prostate cancer with CyberKnife treatment. So I pop this quote in here. I don't need to read it to you because I hope we can all read. A bit of an older paper, but it just articulates quite well why the work's important, because we use high doses in radiotherapy for some types of cancer treatment because it is really effective. But using high dose, obviously, we have higher risk to critical structures that are surrounding and irradiation of healthy surrounding tissue. So we want to treat with the maximum precision possible. So that brings me to the work that I'm doing at the moment. Traditionally with CyberKnife treatment, prostate cancer patients are implanted with usually 4 gold seeds, the fiducials. That allows periodic imaging to pick up the placement of the fiducials and send back in the 3-dimensional plane and also in rotations about the 3 axes back to CyberKnife, so that CyberKnife then can correct its positioning for any internal organ motion that occurs whilst the patient is being radiated. And down here is just an example from one patient that had a fair bit of movement of the corrections that are being made by CyberKnife during fraction delivery. So at the moment, the CTV to PVT margins are usually between 3 and 5 mil, and this is based on the current literature. Those margins actually allow for several sources of error. Only one is the one that I'm looking at, which is the intrafractional motion. At the moment, we are using imaging frequencies for CyberKnife treatments for prostate cancer specifically between 20 and 45 seconds. Imaging does give some extra radiation dose to the patient, and the margins obviously give extra radiation dose to the healthy tissue. So whilst the motion that occurs during a patient's treatment does not cause dose miss because it's continually moving, it does cause dose blurring, so there may be less dose delivered to certain parts of the clinical target volume. So optimizing both the margins and the imaging frequency will help us to treat with precision. It helps improve treatment outcomes. So, we basically, back to that first statement of having the highest chance of relapse-free survival. And also we want to minimize the extra radiation we give to the patient to improve their quality of life after and potentially extend the life of our equipment. So the aims of my work specifically have been to have a look, compile the data, look at how much patients are moving whilst they're being treated, to try and identify if some patients are moving more than others, what some clinical features may be that we can use to possibly predict patients that may be more at risk of movement, and to provide feedback on the optimal combination of margin and imaging frequency. So I've been out here for a little while already due to the graduate program. So for me, I am between here and here, looking at the covariate factors and finding the optimal combinations for margin and imaging, and also somewhere between here and here where a lot of the data analysis has been completed, looking at constructing a predictive model, and then moving into the presentation of all of the results. So I'm going to take you a little bit through what I've done so far. I've extracted the data from Precision. I compiled it using Power Query, which is something I was actually reasonably familiar with from my last rotation with the Department of Health, and put it in a CSV file so that it could be read by Python, and this took up probably the first month or so, if not more, of the project. CyberKnife gives us positional data, so to get the magnitude of each shift, we just take the difference. So I've just basically in Python created some columns that take the difference. Here I've just got a pretty plot of the mean displacement of each fraction that's been treated with CyberKnife. That was on my poster that I just did on Thursday. Got People's Choice. It wasn't because I invited all my friends, not at all. This is a compilation of X, Y, and Z planes, of superior, inferior, left, right, posterior, anterior, of all the points in the data. This is great. It tells us that 95% of the shifts are within these points you can see here. However, just looking at this alone, we don't know which patients are making up these outside points. So this is good, but also it gives us limited information. So I next move on to grouping the data and looking at the range across all of the patients and looking at their 95th percentiles. So this is an example of that just in the superior to inferior plane, and that is only taken from the 45-second imaging intervals. And at the top you can see where I've compiled that. There's more work going on here at the moment. Left to right shifts are quite high, definitely not in line with where the literature says the most amount of movement occurs for the prostate, so I would like to investigate that a little bit further as to why I'm getting such large figures there. Right, so this is actually a plot of the average time it's taken for each person to move 1 millimetre. I put this together the other day actually because I found it in another paper, and that was the approach that they had taken. A paper from Curtis, Curtis, ETAL 2012, where specific information was given on the combination between margins and imaging frequency, which is actually quite hard to find. Papers cover margins. There's some papers that talk about imaging. There's very limited research that's been done on the ideal combination between the two. So according to that paper, the shift for the ideal imaging frequency for 1 mil thresholds or margins was 15 seconds, for 2 was 60 seconds, and for 3 was, I've written 3 here, so that's not 100, I think it was around 200 seconds. I don't know why I've written 3 seconds. This is good. However, the problem with this is this approach calculating the total radial distance and calculating the entire time of the treatment. It doesn't treat oscillations, which may be really small, and large shifts in one direction differently. That's giving me the same, it could be completely made up of a patient that's just oscillating in a very small magnitude. So interesting to look at, however, moving forward, need to look at a little bit more detail. So looking specifically at each shift, the imaging frequencies that we've got are 15, 20, 45 for the most part. There are 2 ways that I can gather the imaging data from my data set. One is the imaging frequency that the radiation therapist selected at that particular beam delivery. The next is what's called the image age, which is taken from the time that's provided at the end of the last beam delivery. And this is a more continuous column because the reality is that the radiation therapist might set it at 15 seconds, but CyberKnife can't image while the beam's being delivered, so it might range from 12 to 17, 18, the actual time that has passed between the 2 images. So this gives a bit more of a continuous data set. So moving forward to try and generate some data to use it in a predictive model for predicting patient shift. I grabbed this data initially and I created a loop which took the factors of each imaging interval that I wanted to use from here. So you'll notice all of these are some multiple of one of these. The second approach I took, which I'm still working on now, is I looked at that imaging age and I grouped it into blocks of 10 to get some categorical data. The first machining model I made had the target variable of patients' time 95% being over or under a threshold. These are the initial... You're right, Keaton. Okay. This took 4 target variables, so the customized imaging frequencies that I had made, margins, I've tried 5 different margins, the age and the weight, and I got a really reasonably nice balanced binary variable for that. Performance of the first model was really not too bad. However, the problem with this, as you can see, is it's really learning mostly off of the margin. So I have really not a lot of way of knowing what's going on with these other features and how predictive they are. So I took it out. And this is the performance just with a logistical regression. There's a few models I'm using on the data, but I'm just showing you this for today, of the imaging frequency, the age of the patient, the weight of the patient. You can see the performance significantly drops off. And considering if it's about 50%, that's the chance that we're going to get when predicting a binary variable. It's not learning enough from that data. The other problem I have with using the factors is the fact that imaging protocol changed between 15 and 20 seconds about halfway through the data set from the installation of CyberKnife, which means factors like, multiples like 30 seconds are only pulling from this patient set, multiples like 40 seconds are only pulling from here. So that could potentially be causing some biases in the model. So at the moment, I am looking at possibly grouping the times rather than saying this is what happens at 15 seconds. I'd be looking at providing probably some windows of time to try and generalize it a little and see if that makes any difference to the model performance. The second thing that we would like to do is to gain rectal and bladder volumes, as they are likely to be more significant predictors than age and weight. So next steps, I would like to play around with that imaging interval as a feature as part of the model, rectal and bladder volumes. I did come across a paper a few days ago that talked a little bit more in detail about the rotations that are going on with the prostate while it's being treated. And I do have that data. It's just a little bit harder to work with because each prostate is a different size, is into deciding the rotation generically across all of them, what's going to be acceptable, what's out of the field and what's inside the field. And then I need to move on to documenting this and compiling not just my results, but also the methods I took to put the data together. So those are some of the references. I would also like to, I don't have a slide in there, I do want to give some thank yous, actually, some acknowledgements. So obviously, thank you to Martin, Godfrey and Gosha, who are my supervisors for the project. Other contributions, Pejman, who's always there to help out, very supportive. Islan, who's the manager in the office where I work at the moment, and Fiona for her contributions to the data for 8 and wage. Satvinder, who gave some suggestions early in the project. Very grateful to the Department of Health and their graduate program for the opportunity to come out here. They basically allowed me in something that was meant to be very generic across the health program and go to where I wanted to work specifically. And not only did they allow me to do that, they allowed me to stay out here for longer than I was supposed to. So very grateful for that opportunity. And a big, big thank you to the machine learning group at UWA, because they are always giving me suggestions and helping me with my work. collaboration. And that's it. Any questions? I got excited. I just saw 15 seconds and 5, and I was. Yeah.
So you're showing that binary data that it was 0.68 and then 0.7. Yeah. So what's is there a score you're specifically aiming for, above 90 or something like that?
That's a very good question. Yeah, I would think above 90 would be great. Yeah.
Is there a standard in papers?
Not that I've come across, especially not for this in particular. That is something I'd probably need to do a little bit more research on myself as to at which point can we, what level of accuracy can we actually clinically implement it. But it's definitely not going to be 0.68. So we definitely need to make it better. And it may be that the features are not predictive enough and then it won't be implemented, but we've at least explored that.
Are you planning on trying to use any different models? Because
Yes.
0.68 performance for logistic regression is not too bad for logistic regression, I think.
So I haven't run, since removing that other feature, I've got 2 models sitting in my script that I used before, and they did have a much higher accuracy. One is the sklearn gradient boosting classifier, and the other was the XGBoost classifier. The XGBoost had a very high accuracy to the point where I was questioning why it was so accurate. It's 95%, and I was like, this can't be right. So yeah, that actually what I will do is run it on those 3 as well, but I haven't had a chance to do that since the other week.
Also, follow-up, have you looked at the feature importance for this one yet?
No.
Okay, no worries.
I'd be interested to know which of those it's using to learn predominantly.
Yes. Yeah. Yeah.
Do you know what the accuracy and precision of the motion movements is?
What do you mean?
So if it's if he records a 1 mil shift,
Ah,
how close to a mil is it?
I believe.
Certainty is there.
I believe, so I asked Gosha about this the other day, and I believe her response was 0.01. It's very accurate, the CyberKnife.
Is she quoting the manufacturer, or is she done a measurement on that?
I think that's the manufacturer. But I will need to, don't take my word for that, I will need to confirm that. Yeah.
Thanks very much.